All right. Good afternoon, everybody. So this is going to be our only class for the week because Thursday is Thanksgiving. So depending on how far I get today, we'll see if I have to cover some new stuff still next week, Tuesday. So of course, I'll have one day reserved for exam review. I may have to cut into the Tuesday class a little bit with material if I don't finish too much today. Um, the homework assignment 7, I'm going to probably have that PDF for 7 sometime tonight. I didn't get a chance to get it done beforehand, but it's going to basically cover Dijkstra's algorithm, Kruskal's algorithm, and the two algorithms I'm going to cover today, and I may cover one of them next week. So we still have this matrix multiplication chaining, and Bellman-Ford's shortest path algorithm will also be on that homework. So nothing really too shocking. Just go ahead and practice those problems. It'll be due next week, Friday, so plenty of time to work on it. And also at the same time, it does help you prepare for the final exam. So definitely not the worst thing in the world. So I'm going to go ahead now and just move a little quicker and go straight to the last time's content. Sorry, screen share. Alrighty. So last time's content, we just mostly talked about, well, we have the following matrices, A, B, C, and D, with their own dimensions, and you want to find the most efficient way to multiply them. So matrices, of course, have this associative property where we can multiply, A times B first, then C times D, and then multiply the combination of these two together, or we could do B times C first, then the result of this, multiply that to D, and then result of that multiplied to A. Either way, the same result will be computed, but the difference is the amount of multiplications will be different. This one had 144, this one had 232. And the trick to doing these is, well, we have the dimensions, let's say A times B. So the amount of multiplications needed for A times B would just be 2 times 4 times 3 because we have 2 rows in A and 3 columns in B. So the rows in A multiply to the columns of B, and there's 4 elements so there's 4 elements in each row of A and 4 columns in B. So we do 4 multiplications and do it for each row and each column of B. So 2 times 4 times 3 is the amount of total multiplications that we're going to do. So we're not really going to look at what's actually inside of A and B. We just only have their dimensions. You want to sort of count how many multiplications we're going to do to compute A times B. And likewise for C times D is 3 times 6 times 5. And then the result, if I have A times B, the result of this matrix is going to be a 2 by 3 matrix. And C times D, that result will be a 3 by 5 matrix. So the result of A times B multiplied by C times D is going to be just 2 times 3 times 5. So you add up all these 3 multiplications together, that's going to kind of compute how many total multiplications are needed for this particular instance. And then same thing for this one. We have B times C first, so it'll be 4 times 4 by 3 by 6. And the result of this matrix, B times C, is going to be a 4 by 6 matrix. Multiply that to a 6 by 5 matrix, we're going to have this many multiplications, 4 times 3 times 5. And the result of this is going to be a 4 by 5 matrix. Multiply that to a 2 by 4 matrix, which will be this multiplication right there at the very bottom. This right there. And then we add up these 3 numbers together to get our result. So we saw here that either way we get the same answer, same product matrix, but the amount of multiplications is different. So you want to find an efficient way we want to find sort of the best possible sort of association or best possible sort of order. So obviously this order was the better one, but is there also better than this one as well? So we're going to actually do this using dynamic programming because we're going to try to construct every possible solution, but we're not going to recompute every possible solution, but simply store it into a matrix, and we're going to reuse old solutions to construct new solutions. So we're going to try every possibility, just we're going to have an advancement over using recursion on this, because otherwise recursion would be exponentially many functions would be called, if you want to try every possible combination of these matrices. So for our dynamic programming approach, which I'll just go ahead and discuss right here, have our dynamic programming approach. Okay. So we're going to use the following matrix. I'm going to go ahead and copy and paste this so I can kind of use this kind of as a guide to help me with this problem. I'm going to go ahead and copy and paste this right over here. So we're going to work this problem out, but we're going to try to find the best possible solution. So we're going to have this sort of M matrix, which is sort of, I think, used in the book or wherever I looked up the problem, used M as our matrix. So we're going to have the following. So I'm going to have, let's say, I'm going to use blue indices here. So we're going to have 1, 2, 3, and 4. 1, 2, 3, and 4. And we can sort of label these as really just 1, 2, 3, and 4 as well. So we're going to have this M matrix over here. So we're going to store all the previous results. Now, this second matrix I'm going to have is not really as important, but it's going to be used to actually construct a solution if you want to. So I'm going to go ahead and put this over here as well. So I'm going to go ahead and do the example, and now I'll go ahead and I'll outline sort of the program for this. But anyway, here we go. So basically, what this matrix really tells us is, for example, this cell right here is going to tell us the amount of multiplications to multiply 1 with itself. Because I guess we can think of as A as just 1. It's going to be this first matrix right here. So obviously, it's going to be 0. Because really, we already have, so 1 is going to really be A in this case. And really, multiplying one matrix to itself, we don't have to do any work, actually. So this main diagonal is going to be just zeros. Because really, the way this reads is, so for example, this cell right there, it tells us that the amount of multiplications needed to multiply matrix 4 with itself, or multiply matrix 4 to get itself. So really, to get the result of D, we don't have to multiply. We already have D's answer. So basically, nothing has to be done there. Now, these ones will be X'd out because they're actually, you cannot multiply. For example, you can't multiply matrix 2 with 1 in that order because matrix multiplication is not cumulative. So I can do A times B, I can't do B times A. So these will be kind of empty over here. So obviously main diagonal, because to multiply to get A, we don't have to multiply. We already have our answer A. So that's why these main diagonal will contain all zeros. So now I want to go ahead and we have to compute these in this order. We're going to first do these, then we're going to do this, and we're going to go ahead and do this. So we're kind of going in this order, basically. Let me just draw the lines over here. We're going to do it in this kind of order. We're going to be doing these 3, then we're going to do these 2, and then we're going to do this last one. That's the order in which we actually work this out. So pretty much we're going to have to store the previous results to compute new ones. Okay, let's go ahead and just sort of work this one out. So I want to go ahead and compute the amount of multiplications needed to multiply M1 with M2. So I want to go ahead and compute the following. Well, that one's kind of trivial because really we're multiplying A with B. So it's going to be just simply 2 times 4 times 3. I mean, there's no better way you can do this besides that. So the result of this is going to be, I believe, 24. So what we do is to construct, so multiplying A times B, or M1, so 1 with 2, there's 24 multiplications needed. And that's the best we can do. And there's really nothing better because, well, A times B, we can't improve that really. So that's pretty much that. So now I want to go ahead and I want to compute M2, so M2 comma 3. So I want to compute the amount of multiplications needed to multiply M2 with, multiply matrix 2 with 3, or B times C. So in this case, we have 4 by 3 by 6. So 4 times 3 times 6, because remember what we do is we have 4 rows, 6 columns. This number 3 is in common. So remember, it's 4 times 6, and there's 3 elements in B's. There's 3 rows in B and 3 columns in C. So that's just the method of getting that. So the idea is that they share this in common. That's like the real trick to this. It was 4 times 3 times 6. In the other example, it shared these in common. So 2 times 4 times 3. So it's kind of a really very simple trick to do this. So basically for M23, that's going to give us the value of 72. If you work this one out, so I think it's 12 times 6, so it's 72. And then we have to compute this one. So we're just simply multiplying this A times B, then B times C, and then C times D, and we're storing these results in this matrix. So we're going to have now M3 comma 4. Well, that's going to be 3 times 6 times 5. So 3 times 6 times 5. And that's going to give us a total of 90, I believe. So I've computed this earlier, so correct me if I'm wrong, but that should be 90. Yes, because 6 times 5 is 30. Okay, so that's 90. So far we have these results. And I'm going to also, in my S array, I'm going to also put these over here as well. So I'm going to also mark these as 0. And X is over here. And I'm going to go ahead and just, for now, put this as 1, 2, and 3. And the reason why is, well, I guess this first sort of column here is kind of difficult to explain. So the idea is we're multiplying, so these numbers are going to be our cutoff points. So really, multiplying A times B, then we chose 1 as our cutoff point. Multiplying B times C, we chose 2 as our cutoff point. And then multiplying 3 times 4, we chose 3 as our cutoff point. So we'll have a better example in a second where we can see what's going on. This is mostly used just to be able to construct our final solution. So far all we did is we just simply computed the amount of multiplications needed to multiply A times B, and then separately B times C, and then separately C times D. We first want to have those pairs. So from there, we can go ahead and we can branch off. We can construct more solutions from that, because we may have to reuse the result of A times B to construct any more solutions. So we'll see an example of this actually right now, because we're about to do that. So now I want to go ahead and compute M1 comma 3. I want to compute this one next. So basically, I want to compute the result of multiplying A times B times C. That's what M comma 3 means, because we have 1 is A, 2 is B, and 3 is C. So I want to go ahead and figure out the best way to multiply A times B times C. So remember, there's really 2 ways we can do this. Either, maybe I'll use violet right here. Either we can have B times C and multiply the result to A, or we can say we can do our cutoff point right here. Actually, I'll put the cutoff point here. We can either have it where we take A times B, and that result multiplies to C. So there's 2 ways we can do this actually. So what's going to happen is the following. I'm going to say M11 plus M23. And there'll be an extra plus, but I'm going to add that in a second. And then we also have another way of doing this. We also can say M12 plus M33. Okay, let's go ahead and just, I'm going to zoom out for a second. Let's go ahead and try to make sense of what are we doing actually here. So, in this example, I'm doing the following. So this first part right here, I'm going to put a plus over here as well. The first part, this portion right there, I'm doing the following. I'm doing this basically. So M11 is the amount of ways to get A, which is there's really 0 ways of doing this actually. And then plus the result of plus the multiplication of B times C, which we don't have to recompute this because we already have the result for that. We already computed earlier. We know what that answer. We know the amount of multiplications needed to get B times C. We already have it stored right there. So it's 72. So basically, what happens now is the following. The result of this matrix is going to be 4 by 6. And we're going to multiply it to a 2 by 4 matrix. So what's going to happen is we're going to have 2 by 4 by 6. Let's just first think about this. So in this example, because I chose this number 1 right there, because of that, then 1 is my cutoff point. So that means we're going to multiply B times C and then multiply the result to A. So B times C, we already have that number stored right there. That's what M23 is. We already had that stored. So we don't have to recompute it. We just take 72. And M11, well, that's going to be 0. And then B times C, the result of this, is going to be a 4 by 6 matrix, yes? And then A is still 2 by 4. So we have to take the result of a B times C matrix, which is 4 by 6, multiply that with 2 by 4. So the result will be, well, 2 by 4 by 6. So the result is going to actually be, in this case, is going to be, let me see, maybe double check this, M13 contains 60. That's the result of this because we're going to really just, I'll write this out actually first. So M11 is 0 plus M23 in our matrix. Here we have M23 as 72. Did I make a mistake here and multiply it by plus 2 by 4 by 6. So M13, we actually should compute this first. So this is going to be 72 plus, let's see, 24, 48. So 72 plus 40. I'm going to try to do long addition over here. So 0, 120 is the result of this, I believe. Just correct me if I'm wrong. I guess that's what I got, 120. So 0 plus 72. 2 times 4 is 8 times 6. Yeah, it's going to be, wait, hold on. That's 8 times 6 is 48. 72 plus 48. Yeah, that's 120. Okay. So anyway, we get 120 right there. And then what's going to happen is now we have to also compute the other case because, well, what about this case? So because we're going to choose 2 over here instead, our cutoff point will now be over there. So we're going to now have the case where I'm going to take A times B, multiply it to C. So M1 comma 2 is the result of multiplying A times B, multiplying matrix 1 with matrix 2. And we already have it stored right there. We already have it. We don't have to recompute that because our matrix already has that number right there. Awesome. And M33, well, that's going to be just simply 0. So, and then plus, let's take a look at this. This matrix right here, if I multiply A times B, we are going to get a 2 by 3 matrix. It's going to be the result of multiplying A times B. And then C is going to be 3 by 6. So it's going to be plus 2 times 3 times 6. So M12 contains the value, let me just take a look at This is 24 plus M33 is 0 plus, let's see, we have 6, so 36 we have over here. This gives us a value of 60. So this one is for the win. That's a better answer. So for M1 comma 3, we have two ways of doing this, and we're going to pick the better one. So the better one is 60. So I'm going to go ahead and put 60 over here. So M13, it's 60, and I'm going to put 2 over here. So for M13, we chose 2 for our cutoff point, our cutoff cutoff point basically. So we broke it at after 2. So to construct M13, we chose 2, which means that we took A times B first and then multiplied to C. So we know exactly where we set that cutoff point basically. So that's what we have so far at least. So now we have to go ahead and compute this value right here, M24. So we're going to have M2 comma 4. So for this one, I want to compute this result basically. I want to compute that answer. So B times C times D. So once again, well, we have two options. I can put a cutoff point here and multiply these two matrices together. Take C times D and multiply result to B. So the way it's going to look is we're going to say, well, M22 plus M34, and then plus we'll have some result. So let me zoom out for a second so we can see all this. Maybe I shouldn't zoom out because I think it's going to be kind of weird. Maybe I'll just bounce back and forth on my screen instead. Oops. I might just sort of bounce around. But I'll zoom out a little bit though. Okay. So in this case, I'm saying M22 plus M34. So right now, I chose 2 as my cutoff point, which means that I'm going to take after M2, which is going to be B, I draw a line right there, and then the result is multiply C times D, and the result of that multiplies to B. So obviously to get M22, to get B, we don't need to do any multiplication for that because we already have B. And then M34, C times D, we already computed that earlier. We did that in our first step. So M34, which I think that's what I'm looking at, 34, is going to really just be 90. So we're going to take the value of 0 plus 90, and then the result is, if I do it like this, what happens is C times D is going to be a 3 by 5 matrix at the end. And then B is going to be, well, it's still 4 by 3. So the result of multiplying B to the result of B times C is going to be 4 times 3 times 5. So the result is going to be 0 plus M34, which is 90, plus, let me see, so 4 times 3 is 12. 12 times 5 is 60, I believe. That's going to be 150. Okay, that was one way of doing this. But of course, with these three matrices, A, B, and or B, C, and D, I could have chosen my cutoff point to be right here, multiplying B and C together, and the result multiplies to D. So this time around, I chose, I can do the following. I can say this as well. I could say M23 plus M44. So here, I picked 3 as my cutoff point, which means after matrix 3, I sort of put that right parenthesis, I kind of stick it right there, basically, which means that now I have B times C, multiply result to D. So B times C, I don't have to recompute that because I already have it stored right over here. I already have M2 comma 3, that's going to be 72. I already have that stored. I computed this earlier, so I don't have to recompute that. It's right there. And M44, well, that's 0. So now we have to get the final result or final product here because multiplying B times C, the result is going to be a 4 by 6 matrix. That's the result of multiplying B times C. And we're going to multiply this to a 6 by 5 matrix because that's what D is. So it's going to be 4 times 6 times 5 is the result. Because what we're doing basically, 4 times 6 times 5, we're first going to compute B times C, and then compute D, and the result of that is going to be a 4 by 6 multiplied to a 6 by 5, which is going to be this many multiplications to do that. Because we have to multiply the result. You have M23, you have M44, those two matrices together. We have to multiply those two together at the end, and that's going to require this many multiplications. Let's go ahead and compute this one. So in this example, M2 comma 3 is going to be 72. M4 comma 4 is 0. And then plus, let's see. So you have 4 times 6 times 5. So let's take a look. So we have, I think it's going to be 100 and, hold on. 4 times 5 is going to be 20. It's 120. This will be 192, I believe. So obviously, the better one is going to be this approach. You want to pick the better of the two. Because we have two ways of doing this. So we can see here, we either could have done, we could do either this, C times D first, and then multiply it by B, or we could do B times C first, multiply it by D. There's two ways we can do this, and the better way was when we chose, this one. That's the better way, when we chose 2 as our cutoff point. So for M24, I'm going to put 2 over here. Because choosing 2 for a cutoff point is the better result, which means that we cut off right there. So C times D multiplied by B, that gave us fewer amount of multiplications. So now we're actually almost done with this problem because actually I should put this here, 150 goes right there. So our final answer is going to be right here. Whatever this is, that's our answer. So we can see here, this matrix just sort of stores our previous results. You don't have to constantly recompute because if you do recursively, you have to keep recomputing, which is going to take a lot of time. It will be exponential ways we're going to be doing this. So this way is definitely a lot better because you have to keep recomputing every single time. So now we have to find our final result, which will be M1 comma 4. Put it right here. M1 comma 4, which is going to be our total final answer, which is basically M1 comma 4 is really the multiplication of multiplying matrix A, B, C, and D. We have to compute these because there's many ways we can do this. So the first way is we could say, well, I could choose 1 for my cutoff point. Or I can choose 2 for my cutoff point. Or I could choose 3 for my cutoff point. So there's 3 ways we can actually do this, and we don't have to recompute because all of these results we already have. So M2 comma 4 is the amount of ways we can, or sort of the optimal many ways to multiply matrix 2 with 4. We already computed that earlier. We have it right here, actually. We already have that answer. So we can reuse old answers. Let's go ahead and sort of work this out. So if I use 1 for my cutoff point in this example, that means I'm going to draw a line right here, which means that I'm going to multiply B times C times D, and then the result, multiply it to A. So B times C times D, which is M24, we already know the answer to that. It's right here. We already found the best way to multiply matrices 2, 3, and 4, or B, C, and D. We already know how, we already have the best way, it's actually 150 is the best way we can do this. We don't have to recompute that. We already know the answer. We stored it in our matrix, in this matrix right here for M matrix. So M11 is going to be 0. M24 is going to be 150, sorry. So now we have the following scenario. So A is going to be a 2 by 4 matrix. And this matrix, so M24, so B times C times D, well, this is going to give us basically a 4 by 5 matrix. Because remember, we first took these two, which will be 4 by 6, and 4 by 6 by 6 by 5, this will be 4 by 5 matrix. And the shortcut here is really just the outer numbers really is our shortcut. Because 4 by 3 with 3 by 6 is 4 by 6, and then 4 by 6 with 6 by 5 is 4 by 5. So that's going to be our result. So multiplying B, C, and D, no matter what we do, the result is going to be a 4 by 5 matrix. We multiply that to A, which is 2 by 4, so 2 times 4 times 5 is the extra work. Because what we did was we first had to compute all the amount of ways to get A, which is 0, plus the amount of multiplications to get B times C times D. Once you have those two matrices, then the result is you have to multiply A with the result of B times C times D, which is 2 by 4 with a 4 by 5 to give us this answer. Let's go ahead and work this one out. So M11 is 0. M24 from our matrix is going to be 150. We can read that from our results. So it's going to be 150 plus 2 times 4 times 5. So I believe this is going to give us, I think, 40, because 2 times 4 is 8. Multiplied by 5 is 40, I believe. So we get 190. So that's going to be how many multiplications we're going to have if we multiply it, if we do this type of work. But of course, this is not the only way we can do this, because we have this way. We could say we can have 2 as our cutoff point this time around instead of 1. So if I do this approach, then here's going to be our representation. We're going to draw a cutoff right here, which means you're going to have this scenario. We drew that right. We put a cutoff there. So we're going to have A times B multiplied by C times D because we chose 2 as our cutoff in this example. And once again, the beauty of dynamic programming is that we already know the result of A times B. We already computed that. That's right here. So M12 is right there. We already know it's 24. There's 24 multiplications to be done. If I multiply A times B, I don't have to recompute that. I already know the answer. It's 24. Awesome. And then M34, well, we also know that answer. It's 90. So multiplying C times D, we already know it's 90. We store that result. Awesome. That's pretty cool. And now the result of A times B is going to be a 2 by 3 matrix. And the result of C times D is going to be a 3 by 5 matrix. So multiply these two resulting matrices together, it's going to be 2 times 3 times 5, because this number right there is in common among these two. So 2 times 3 times 5. So the answer here is going to be 24 plus 90 plus 2 times 2 times 5. So we have 30, I believe, because 6 times 5 is 30, okay? And then we're going to have 144, I believe, is the result of this, because 90 plus 30 is 120. 120 plus 24 is 144. So this actually is better than, so if we choose 2 for a cutoff, so this approach is actually better than just saying B times C times D, and that result will apply to A. This is actually better, this other approach. But you still have one more approach left. We could, of course, have m 1, 3 plus m 4, 4, which means in this example, we're going to draw the cutoff like this. We're going to have 3 for the cutoff, which means we're going to do this basically. Because this case, we chose 3 for cutoffs. Notice we chose 1 for a cutoff, then 2, and then 3. Now we're choosing 3 for our cutoff because we have this final method. This could be the better method, maybe. I don't know. So this a times b times c, or other words, m 1, 3, we know the answer to that already. We already computed that earlier. It's going to be 60. We know the answer to that. That's pretty cool. And then multiplying to get d, well, there actually requires no multiplications to get that, because 4, 4 is 0. We already know the answer to that, so we have those. So now we have to go ahead and get the final product. So if I take a times b times c, the result is going to be a 2 by 6 matrix. And you can work it out because if I take these two first, it'll be 2 by 3. Then 2 by 3 with 3 by 6 will be 2 by 6. So I guess the shortcut really is just the outer numbers is our shortcut to do this, really. And then we're going to have a 6 by 5 matrix with D. So the same pattern, it's 2 times 6 times 5. Okay, so M1, 3, it's 60. M4, 4 is 0. And then plus 2 times 6 times 5, that's going to give us, I believe, 60. Yeah, because 2 times 5 is, yeah, because 6 times 5 is 30, plus times 2 is 60, so it's 60. And that gives us 120. And that is actually the smallest among all three. So 120 for the win, because you want to pick the smallest one. Let me go ahead and write 120 right here. And we used 3 as our cutoff point. So I'm going to go ahead and put 3 over here. But the real important answer is the following. This is going to be, I'm going to put this in gold because, of course, again, gold for the win. That's our answer. I'll erase all of this stuff. So I guess this one's kind of not in the way. But that's our answer. So the best we can do, multiplying a times b times c times d, the fewest amount of multiplications we can do is 120. That's our answer. And then this number here, this 3, is a way to kind of compute or construct our solution. So a 3 here means that it will multiply a times b times c times d. So the whole product, I'll put this here. So a times b times c times d. So the whole entire answer from m1, 4, we actually broke it like this initially. So that 3 means we chose this as our cutoff point. And to compute m1, 3, we chose 2 as our cutoff point. So, and then of course to compute 1, 2, we just pick 1 as a cutoff point, which doesn't really matter because for 2 matrices, that's all we can do. So this is sort of what we constructed. And if you go ahead and work this one out, let me just see, we got this correct. Yes, I did. So this is going to give us 120 if you multiply in this fashion. So this S matrix will kind of give us our solution. So we first, to get M1, 4, we picked 3 for our cutoff point. And then to get M1, 3, we chose 2 for our cutoff point. So that's how we sort of construct this. I mean, maybe I'll do this again just to kind of be a bit more automated over here. Just maybe I kind of went a little bit not really automated enough. So you first look at this number, 3. So we chose 3 for our cutoff point. And since we chose 3, then that means we have m1 comma 3 plus m4 comma 4. So m1 comma 3 is right there. This is, this is 1 and 3. So m1 comma 3, we use 2 as our cutoff point, so we close it right there, like that. And then to get m1 comma 2, we chose 1, but really between two matrices, there's no real cutoff points. So there. So this is going to be our answer is 120, and that's going to be our sort of our answers as to how to get 120. So this is kind of how we do this. So this is, this is the outcome right there. And pretty much, I guess the dynamic programming solution, I guess the actual code for this is as follows. So we have m I comma j is going to be the minimum of, I believe, I less than or equal. Hold on. Maybe I'll zoom in a little bit so I can actually write this a little bit nicer. So we have I less than or equal to k less than j m I k plus m k plus 1 j plus d I minus 1 multiplied by dk multiplied by dj. And basically, here's how we can look at these d values. So let me just go up here for a second. This will be d0, d1, d2, d3, 4, d5, d6, and d7. Let me double check to make sure I got those indices correct. Oh, so I made a mistake. Yeah, I'm sorry. Messed this up. Essentially, d0 is this. d1 is going to be basically this 4. And d2 is going to be 3. Actually, d2 is going to be, let me just double check. Hold on. Yeah. So d2 is going to be that 3. Then d3 is this 6. And d4 is that 5 at the end. I'll put this over here, same thing. There. So that's the right idea. So now, I guess that's if you were to code this, you would have it like that. But of course, you can just sort of follow the example I did here. So for the homework and the exam, it would be the same exact problem, except different dimensions for A, B, C, and D, but the same problem. So of course, you can follow these notes. You can follow the video because it'll be recorded, obviously. So you can follow this to help you with this. So alrighty then. So let's go over the runtime analysis of this. So basically, very simple to see the runtime analysis. Initially, all of these are going to be just sort of 0 in runtime. And notice over here, we're going to do for m1 comma 3, we sort of do 2 amounts of work. So the idea, this is going to sort of follow the Gauss's formula. So you first do 0 or do 1 amount of work plus 2 plus 3, because you can see here, these get larger each time. Here we only have just like that. So basically, we see that's going to follow Gauss's formula in terms of the pattern or amount of steps it will take. Because you can see here, this is going to involve sort of a loop. So you first have to compute all of these in 1, 3, 2, 4, 1, 4 like this. So it's O of n squared. It's runtime. It's O of n squared. Where n is going to be the amount of matrices you have, pretty much. So there we go. That's going to be our other sort of dynamic programming algorithm. So for homework, just, I'll give you a different set of matrices. You have to sort of show me the table and show me the work and all that. So, of course, you want to show me the final result. You want to also show this. I'll box this in as well because you definitely want to show this because this is how you actually got this answer. But basically, it depends on the cutoff points that were chosen. So each time, in this case, we chose 2 for the cutoff point. Here we chose 2 again. And here we chose 3. So that's how we kind of can construct this. So we first chose 3 as a cutoff point, then 2, and I guess 2 over here as well. So I guess that's the idea. That's how we kind of constructed this. I don't want to get myself confused right here with this, but it's definitely yeah. So that's we want to follow this approach basically. So it's not too bad. It's a little bit tricky at first. It took me a little bit of time to kind of get the hang of this, but just for homeworking practices, of course, and for exam, of course, you're gonna have to do this as well. So just practice it. It's very mechanical after you do this. It's actually gonna be the same steps. The only difference you're gonna have to do really, I mean, I really think these will be different, obviously, for your homework, but it'll be these steps entirely, same steps you're gonna use. I'm not gonna pick a bigger problem, same problem, just obviously, these will all be different. That's about it. So I guess to make things a bit easier, I suppose. Okay, so now we're going to go over a different problem on dynamic programming, and this might take me the rest of class today. I may have to spend a little bit of time next Tuesday as well on this, but not a very hard problem actually. I think it's a little bit easier than this one, so I guess it's probably the comforting use. It's it's going to be the last algorithm we're going to cover for this course. So that's also some good news actually. We're almost done. Let's cover our last problem. I'm going to of course post these notes up on Canvas. Let's go over Bellman-Ford's algorithm. Bellman-Ford shortest path algorithm. So we covered Dijkstra's algorithm so far in this class. So our last one is going to be Bellman-Ford. I'll probably use maybe kind of a grid so it's easier to draw the graph, I guess. Maybe not. Maybe I'll just use the lines like this. Yeah, good enough. So basically, there's going to be another dynamic programming algorithm. And of course, it's going to be used for, it's going to be also a single source minimum, oops, if I can spell, minimum weight path algorithm. So just like Dijkstra's, it's not going to find every possible pair of shortest paths. It's going to we're going to pick a start node. And with that start node, we're going to find the shortest path to every node in the graph, but only from that start node to every other node. It's not every pair. But the idea here is that it works for negative edges. And another interesting concept, I may not be able to cover this, I don't know for sure, but it also has an improved runtime if the graph is a DAG, which is again short for directed acyclic graph. So the graph is directed and acyclic. It actually has a better runtime than Dijkstra's actually, which is kind of cool. And I guess I was told by a professor that most graph problems are kind of direct acyclic in general, so this actually is pretty applicable. But I'll cover the generic example on this, and if I have time, I'll also go over this improved version if I have time today and Tuesday. I don't want to spend too much. I want to try to at least start doing some exam review maybe even on Tuesday. It would be nice to have more time next week to cover the exam review. So let's go ahead and draw the pseudocode for this algorithm. So we're going to have, I'm going to write this out. So we're going to have, oops, Bellman-Ford. So that's going to be called. And we're going to pass in the graph, W and S. So W is going to be that that weighted array. So similar to the Dijkstra's, except we're going to update this W array multiple times. For Dijkstra's, remember, once we popped a node off of the heap, then we wrote to this W array, and we never wrote to the array ever again. This is going to possibly update W array many times as we go. So anyway, the first thing we're going to do is we're going to initialize all elements in W to be infinity. And of course, W S is going to be 0 initially, because I guess that's going to be your starting node. So you want to have that start at 0. Yeah, start that at 0. And then what's going to happen is we're going to have the following loop. So for I equals 1 to the cardinality of V minus 1. So this loop is going to run V minus 1 number of times. And we're going to have a nested loop. We're going to have a loop right here. It's kind of the Python-ish way of writing this. So for each edge, u, v, in our set of edges, we're going to do a relax. Relax u, v, and w. That's it. I'm going to go ahead and write the relax function, which is pretty simple. So relax u, v, and w. Basically, if w of v plus the edge weight of u to v is less than wv. So you found, oops, supposed to be wu, my mistake. So if you find a better path weight from u to v, or if you found a better path weight, so wv is going to be the path weight from our start node to v. If I found a better one, I'm going to update this. Oops, I'll make it more box like that. And we, of course, could update a predecessor. If you want to have predecessor array to construct the actual path, we could do that as well, but we'll leave that part out. So that's really it. And the key is, well, we don't know. So for each edge, this could be in any order. We can look at any edge. There's no real order in which we have to look at edges. So any edge, so every edge we have in our graph, one at a time, update every single possible node, and we do this again and again. Now, here's another sort of trick to this. So if no relax occurs, then the algorithm can stop immediately. So what we're doing basically is this for loop right here. You go ahead and actually just put this right here. Let me just put a shape here for a second. This for loop. This loop runs v minus 1 number of times, but it could run less than v minus 1 number of times. Because if, let's say, after in our for each loop, so let me go ahead and put this block over here as well. In our for each loop, if we don't relax ever in that loop, that means we're done. That means nothing will ever update again. So at that point, we're just doing the same thing with no new results. So we're kind of being insane according to Einstein at that point. So the idea is if we don't relax, then there's no point to run this. But in the worst possible case, we're going to have to run this v minus 1 number of times because the shortest or the minimal weight path cannot be more than v minus 1 edges in that path. If it's more than that, that means you have a negative cycle in your graph. So the minimum weight path will have no more than v minus 1 edges along that path. But if, of course, if let's say we do this for each loop, and then for every edge, we never have to do relaxation or never have to do relax ever, that means we're done. We can stop. We can break out a loop early. You'll have to run this loop v minus 1 number of times. But in the worst case, that we're going to have to run this for loop v minus 1 number of times, and then we have to iterate through every single edge in our graph. But let's do an example of this, and I'll try to see if I have time to also discuss this as well. Let's first do an example of Bellman-Ford. So I have about 20 minutes or so left, so I may have to cut into class a little bit on Tuesday. Let's go ahead and just work on this one. So the following graph over here, so I borrowed this one from the book once again, because I guess the book is relatively a good source. I mean, the MIT book is a nice book. It's hard, it's impossible to read that book, but it is nice, very technical, except you know, it's unreadable, of course. So we have following graph over here. We have 2 more nodes. Okay. I'm going to have them as, this will be S, this will be A. I'll try to get rid of that ink to shape. We're going to have B. We're going to have C and D. Like that. And then, of course, I'm going to add in these lines. So let's go ahead and add these in. So here's S goes to A. S goes to C. A goes to C as well. See, A goes to B and B goes back to A. Awesome. So I'll redraw this by mistake. Doesn't look too good like that. That's better. And then also B goes back to A as well. All right, and then C goes to B. Pretty extreme graph actually from the book, but you know, I think it does cover a lot of good examples. It covers many cases, I think. So it's definitely a good example to use. A goes to D as well. And then C goes to D. And D goes back to S. Then I'm going to erase this and try this again. I think it kind of cuts into the other line right there. No, it cuts into that one. Okay, let's try one more time. Yes, the key to any graph algorithm is, of course, the first hard step is drawing the graph. And let's see, we have D goes to B. I hope that's it. Please say that's it. So I'm going to go ahead and add in the edges in. Edge weights 1 by 1. So you have 6. This will be 2. This will be 7. This will be 9. This will be 8. We have 5 over here, -2 for that one, -3 for this, 7, -4. I think that covers everything. I mean, let me double check to make sure this graph is the same. So there's So this, we have that. Good. I think we got everything. Awesome. Okay, we got everything. There's our graph. So we have some negative edges, but it's okay. That's not going to cause any problems at all. And I'm going to actually label these. So I'm going to sort of write out the order in which I'm going to process these edges. So really, there's no real order we have to actually use. I'm going to go ahead and just say for now, here's the order we're going to pick. So I'm going to use, this will be, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all the edges we have, right? I think I have this one over here, 11. So I'm going to follow this order. It's definitely almost an abomination now. Oh, wait, actually, I already have this one included right there. Ah, darn, okay. Let's try this again. So you have 1, 2, 3, 4, 5, 6, 7, 8. Maybe 9 over here. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges in total, I believe. 1, 2, 3. Okay, so that's going to be the order in which I'm going to process. So we have this for each loop in Bellman-Ford. We pick any edge. So I'm going to go ahead and try to be consistent and keep this sort of order, basically. So we're first going to pick AB, then BA. Yes, I think that's going to be the right order. That is an order of some sort. Okay. So now we're going to do the following. I'm going to go ahead and draw my W array over here. And it's going to be a relatively small array because we only have 5 elements. This will be our W array. I'm going to go ahead and copy and paste. I'll have to keep on drawing this again and again. So initially, so actually I should put S, A, B, C, and D. Now I'm going to go ahead and copy this. So initially, all these are going to be, except for S, they're going to be all infinity, which means that we have no shortest path so far. We don't know it yet. Okay, so zoom out here. So using our algorithm, we're going to first pick an edge. It's going to be our first pass, basically. Our first pass of Bellman-Ford. Okay. So you're going to first pick an edge. So I guess we'll pick AB first. Okay. So A has a weight of infinity plus 5, which would be infinity. So B's weight is going to be infinity. We can't update B at that point. So that's a bummer, I guess. I'm going to go ahead and use pink to kind of like just sort of cross it off that we already processed. We looked at this edge. Okay. Next edge will be B goes to A. And well, B has the weight of infinity. Minus 2 will be infinity. So A will not be updated. We can't relax A. Okay, fine. Next edge we're going to have is going to be 3. So our index of D goes to B. So D has the weight of infinity plus the weight to B, which is going to be 7, so infinity. So B doesn't get relaxed. The fourth edge, well, that's going to be C goes to B. So C has a weight of infinity plus -3 is still infinity. So B can't update. Oh, well. And then our next one will be A goes to D. So you can kind of see I kind of chose this order to kind of give it the worst possible case scenario. So A goes to D. So A has a weight of infinity plus -4, still infinity. So, oh well. Then step 6, we're going to now look at our next element. So next edge is going to be S goes to C. Okay, S has a weight of 0 plus the edge weight of 7 to C. So C is going to be now updated to 7. So we just relaxed C. So we updated C. And then our next sort of edge, which will be edge 7. So D goes to S, so D is infinity plus 2, still infinity. So, or it doesn't really, it's not going to relax because infinity, because right now S has a weight of 0. So D, which is infinity, plus 2 is infinity, so it's not going to be a better path weight, so we'll keep it like that. I'm going to go ahead and sort of throw this one also. I think I only have just 10. So I'm gonna modify this to be 10, my mistake. I only have 10 edges. So then edge 6, oh, sorry, edge 8, I'm sorry, is going to be S goes to A. S has a weight of 0, because our W array contains 0 for S. Plus 6 is going to be 6, which is less than A's current weight, which is infinity. So updated A to be 6. And then our next edge, we have A has a weight of 6 plus 8 is going to be the weight from A to C, which will be a total of 14. And it's actually better. Actually, that's not better because C has 7, so we didn't find a better one. So we can't relax C because we have a different path to C, but it's going to be A6 plus 8 is 14, which is not better than C7. So we'll keep it like that. And then our last edge process is going to be, well, did it in the wrong order. It's supposed to be this one first, then, okay, it doesn't really matter, actually. It ends up being the same either way. So my mistake. It's supposed to do 9 first, then 10. I'm sorry. So this value right here has a weight of 9. So S has a weight of 7 plus the edge weight 9, 16. So D will have the weight of 16. We're going to relax D. And that's the end of our first pass. Obviously, we're not done because in the worst possible case, since we have 1, 2, 3, 4, 5 nodes, we're going to do at most 4 steps, actually. So that was our first step so far. Okay, let's go ahead and now restart for our next step. So I'm going to go ahead and just paste this over here, so I don't have to redraw all that. I'll put up a little bit like this. This will be our second pass. Oops. Second pass. I'm going to copy everything from our last pass. So we're going to have 0, 6, infinity, 7, and 16. I'm going to go ahead and clear all these out. So we're going to go ahead and restart this entire process. I'm going to be consistent and pick the same edges in the same order. And we're going to redo this. We're going to do this again. Because, oh darn. Because this is in fact going to be a dynamic programming algorithm. So the idea is, right now, all we have is the best paths so far we have from S to A, S to B, S to C, and S to D. And using the S's path to A, we might find better paths later on. So far, each element in this array is just a path weight from S to that node. And using that weight, we're going to try to find better weights later on. So if you look at this relax, we're using WV. So we're using WU plus. So we're using old results to compute new results. So that's going to be the idea here. So a little different from Dijkstra's because Dijkstra's doesn't use old results to compute new. It uses the binary min heap to pop elements off. But here we're using, these are going to be our results, but we're not done yet. I'm going to use these to create new results. So right now, our next step, so we're going to go ahead and run that same pass again. We're going to pick this edge right here, index 1, or this edge right there. So A goes to B. So A has the weight of 6, currently, looking at the array, plus the edge weight 5 is going to be 11, which is actually less than B's current weight, which is infinity. So we're going to update B to 11. We just relax that node. And now we're going to process the next sort of edge, which is going to be B goes to A. So B has a weight of 11 plus -2, which is going to be 9, which is not better than 6's current weight, so we're not going to relax. Next edge, we have 3, which goes from D goes to B. D has the weight of 16, plus 7 is going to be 23, which is not better than B's current weight, so discard that. Our next one will be the edge from C to B. So C has the weight of 7, looking at this array, plus the weight -3 to B. So B has a better weight, actually, now. So B has the weight of 4. We relaxed it. We found a better path. Our next edge is index 5, so we have from A goes to D. A has the weight of 6 plus -4, which is going to be, D is going to be now 3, actually. Or no, sorry. A is 6 plus -4, so 2. So D is going to have the weight of 2. We found a better weight. And we're done with this. So then now, for step, our next element, so it's going to be 6. So S has the weight of 0 plus 7 to C, which is not going to be a better weight because that's not better. So we just don't relax that. And then I'm going to go ahead and put this here. So our next one's going to be 7. So D has the weight of 7 plus 2. It's going to be 9, which is not better than an S. So we're not going to actually relax that. Step 8, well, S has the weight of 0 still, plus the edge weight. The edge weight from S to A is going to be 6, so A doesn't update. Then this one right here, so step 9, we have C goes to D. So C has the weight of 7, plus 9 will be 16, and D is not going to be updated because D has the weight of 2 currently. And our last one is going to be, well, A goes to C. A has the weight of 6 plus 8, which will be 14, which is not better than C's current weight of 7. So we're done with that as well. So after our second pass, this is going to be our result. And really, the order in which we actually looked at edges in our for each loop is going to determine the runtime. So that's going to be our second pass. So I'm going to now, I'm going to erase these. Just going to just kind of quickly do these. Well, I'll do it later. Anyway, that's it for right now. So I'm going to continue on this some more next time. So Thursday is no class, obviously, Thanksgiving. So have an awesome rest of your day. Have an awesome Thanksgiving. Thanks for watching. Take care. And I will see you guys next week, Tuesday.